Okay, so welcome to the official first class that we will have in Calculus 1. So Math 2401, it's a big stepping stone for a lot of you as science majors and as math majors. This course is going to hopefully inspire you to continue on in your science degree and not scare you. I know that when I first took calculus, I made a C and I was really nervous and it wasn't a great experience for me. So hopefully this is not that, all right? So let's go ahead and get started. And hopefully I'm writing big enough for everyone to see. Looks like I am. All right, so traditionally calculus was, well, not traditionally, it was developed in the study of motion of objects. So Isaac Newton and Leibniz and a few others were studying the motions of planets and the motions of objects rolling down hills and things like this. And that's what motivated the study of calculus. And it's a fundamental tool for any scientist, right? However, I think that this view of teaching calculus from there is a view that is out there that I've noticed in all of the textbooks, in all the video lectures that I see on YouTube, in all these materials, that they try to start calculus 1 by motivating it with a tangent line problem or an area problem. Now, I understand why this is done, because it's sort of how calculus came to be. But I think from an understanding point of view, that isn't really necessary until later in the semester. So I'm gonna kind of differ from that. I'm not gonna give you those motivational things. I'm just going to tell you that calculus is different from what you've studied before in that now we're going to look at how things change over time, or how inputs to functions affect how a function changes. And then when we get down to the tangent line problem, for example, then I'll reference this back to maybe something like velocity or acceleration. I'll just go ahead and write that out, just so that you know. So we are interested in behavior functions as the input approaches value. Now, all of you should be familiar with functions, right? You've had to take algebra, trig, pre-cal, these courses. So in these courses you've taken prior to calculus, you've looked at, well, what's the domain? If we plug in values, what's the exact value of the function? In calculus, broadly speaking, we're looking at how the function is going to change as the input changes. So there is this distinction, right? We can forget about motion and velocity and all that stuff and just focus on that one fact, that this course is, broadly speaking, going to involve the behavior of functions as the input changes. And this happens to have a broad range of applications. Okay, so that's the goal of this course. And in order to get to this notion, we need to bridge your understanding of functions to calculus with something called a limit. So I'll just say something like pre-cal. Something, and then calculus. And that's something that we need to cover first is this notion of a limit. So before we can really start talking about the tools of calculus and using the tools of calculus, we need to bridge your understanding between functions and calculus with this idea of limits, okay? So in order to understand limits, so let's write it out. Limits require a few things, right? So one, well, maybe require understanding. Of a few things. Number one, most importantly, is the real number line. Number two, the notion of distance. So the real number line, I'm going to denote by that R, fancy R. And then for two, the notion of distance on the real number line. Okay. And then three, we have to really understand what the Cartesian plane is. And yes, I know that all of you will know that the Cartesian plane is this two-dimensional surface that you plot functions on, but there's a little bit more to it than that. And then finally, I suppose I'll call it sequential thinking. Because that's kind of a vague term there. Okay. So before we can even talk about limits, we need to understand these four concepts really well. And I know that when I was learning calculus, this was kind of glossed over, and only after the fact did I realize how important it was, how fundamental these notions are to understanding limits, which in turn, limits will help you, are the fundamental building block of calculus. So if you don't have this, you can't do the rest. Okay, so we'll start with the real number line. Okay. All right. So hopefully all of you know that the real number line is an ordered sequence of real numbers. In fact, it's a little bit more than that. It is so it's n, something called uncountable. And you don't need to understand what that is. If you're a math major, eventually you will. So it's an uncountable, infinite, ordered sequence of real numbers. It's reals. Okay? And then the most important part here, with no gaps. So I can't emphasize this enough. There are no gaps in the real number line. And we typically denote the real number line as such. Maybe here's like 0, and then negative infinities that way, positive infinities that way. Okay. So what do I mean by no gaps? Technically speaking, it means that the reals are dense. There's a lot of them, right? It kind of relates back to this uncountable notion. So there are several different number systems that you might be familiar with. For example, the counting numbers, like 1, 2, sorry about that. So like the counting numbers are 1, 2, 3, 4, 5, so forth, right? The integers are the positive and negative counting numbers together with 0. The rational numbers, all numbers that can be written as a ratio. Now, with the natural numbers or the counting numbers like 1, 2, 3, 4, so forth, and like 1 and 2, for example, there is no counting number between 1 and 2, right? So they're not dense. There's nothing in between the numbers 1 and 2 that is also a counting number. However, the real numbers are dense. And to state this formally, no gaps mean that for any two reals, say A and B, with A strictly less than B, there is another real, say C, such that A is less than C, which is less than B. For any real numbers that you can think of, no matter how close they are, as long as A is strictly less than B, there is a number between them. Call it C. Now, why is this? Right? So, like, why? Well, it's somewhat obvious to me, but maybe not so obvious to you. And the reason is, I like to think sequentially, that's part 4 here, when dealing with this real number line. So for example, I'm looking at the real number line, call it R, okay? And suppose here's A, and here's B. Okay. Now a part of the review, the algebra review that you might have looked over, you might have seen something called this midpoint formula for the midpoint between 2 points in the Cartesian plane. The same notion applies to the midpoint between 2 numbers on the real number line. So for example, this is A and this is B. This number right here, whatever that number is right there, there's a formula that we have to access that value. In particular, it's what? A plus B over 2. That's that number, okay? So this is an example of if there's any real numbers with A strictly less than B, there is a number in between them, in particular the half, the midpoint between them. So then we can just keep on sequentially applying this. Like if we call this number C, then if we zoom in to here, right? If we zoom into this interval here, then here's C, here's B, we can find the midpoint again, right? Just B plus C over 2. And then we have that value. And then zoom in again, zoom in again, zoom in again. And we can keep on doing this forever. Okay, so this idea of sequentially performing an operation is essential to calculus. And this idea that between any 2 real numbers, we can always find one in between them is also essential to calculus. And in fact, if we keep on having the distance between the 2 points that we're looking at, we're getting what's called infinitesimally small, or infinitesimally close to B. Closer and closer and closer and closer and closer. We can do this forever. Just keep on having, keep on having, keep on having, keep on having. So we've encountered 2 important concepts. There's always a number between any 2 numbers on the real line. And in finding a number that's in between them, we can continue this process to get as close as we want to B, right? We can also do the same thing to A. We can keep on having and get as close as we want to A. So as sort of a implication of this notion that there's no gaps, we have that we can, quote unquote, move as close as we want from one number to another. So that's kind of a implication of this idea that there's no gaps between two numbers on the real line. Now, if you're like really paying attention right now, you'll notice that we're always taking the midpoint between the two numbers as we continue this process forever, right? So if we're always taking the midpoint, we're never going to actually reach B, right? No matter how close we get to it, we're never going to reach B. And if we did it over here, because we're always finding the point in between the 2 points, we're never actually going to get A. But if we're taking midpoints this way, we're approaching A and getting as close as we want. Close, right? And if we go this way, we're getting as close as we want to be. We're getting close, which leads me to my next point. So we've covered the real number line. Next up, the notion of distance. Okay, so distance is so fundamental to everything else that we'll be doing in this semester that we have to take a moment to really make sure that we're all on board. Okay. And we kind of talked about sequentially thinking too. So we just have these two left over. So distance. Okay. So just a moment ago, I was talking about getting close, right? Getting closer and closer and closer to B if we're kind of moving this way from A. We're getting closer and closer to A if we're moving this way from B. But what does it mean to be close? Well, we need a way of measuring distance, right? And the simplest way to do this is by taking the absolute value. So the distance I'll say between, not from. So the distance between two reals, A and B, is, for our purposes, the absolute value of A minus B. Okay. So why would this be an appropriate measure for distance? Well, notice that, so the absolute value is always non-negative, right? It's greater than or equal to 0. So when we were thinking of distance between things, we surely shouldn't have a negative distance to something. So absolute value being greater than or equal to 0 checks that off, right? Moreover, the distance between A and B, so this is equal to 0 if and only if these are the same numbers. A and B are the same numbers. So, okay, the distance between them is 0 only when they're the same number, okay? And there's a third property called the triangle inequality that I won't go into, but this is how you measure distance. So for example, the distance between 4 and 6 is going to be the absolute value of 4 minus 6, which is the absolute value of -2, which is 2. Okay? Which is true, right? If we're looking at the real number line, there are exactly 2 whole spaces between 4 and 6. And so, like, we just draw the number line, there's 4, 5, 6. Right, so there's 1, there's 2. So there's unit distance of 2 between these things. It makes sense, okay? So I really want to emphasize this to you. And I don't think that a lot of students taking calculus really remember this as they're taking the course. That whenever you see this, right there, whenever you see the absolute value of the difference of 2 numbers, it's the distance. It's how far apart those numbers are. Okay? Super, super important, especially when we go into the formal definitions of calculus, including the formal definition of the limit. Because limits are defined formally in terms of distances between things. They don't say distances, they just write absolute values of differences and expect you to know it. But really, that's what it's saying. The distance between this and this implies the distance between this and this is something. Okay. Okay, so we've covered part 2. Next up, we have the Cartesian plane. So all of you should be familiar with this notion. Okay, this Cartesian plane is what you've used in algebra, in trig, in pre-cal. But some of you might not have related it really to the real number line. The Cartesian plane is actually 2 real number lines. That's all it is. So it's 2 real number lines connected at 0 with an orthogonal or 90-degree angle. Okay, and specifically it's this. So here's the real number line we were just looking at, right? That's the real number line we were just looking at. Here's 0, right there. And then there's another real number line here. The Cartesian plane is often written R times R. Every point in this plane is a pair, a tuple, of an entry from this real number line and this real number line. Now, in your previous courses, you might have denoted this axis by Y, or in this axis by X. That's not set in stone. It really is just a real number line and then another one at a right angle with that. When you get to multivariate calculus, there'll be another real number line at a right angle to that. When you get to linear algebra, if you take that course, they're all at right angles and you can have as many as you want. Okay? So these real number lines are meant to represent, well, originally meant to represent spatial coordinates, right? So, for example, we live in 4-dimensional space-time, right? There's 3 dimensions of space, 1 dimension of time. This is a simplified version of that. This axis could represent time in seconds. This could represent distance from home or something like that, right? But it's important to remember that it is exactly two real number lines at a right angle with each other at the origin, at 0 on both of them. Now, why is this important? It's important because, well, it's fundamental to everything, but also the notion of distance is going to apply in one direction and the other, right? So for example, like suppose we had some like function like this, and there's some discontinuity right there, right? And that discontinuity happens at C, then there's some distance around it, and some, I'll call this discontinuity, the value where it's missing, I'll call it L, there's some distance around that. Which actually makes me think that I should probably say one more thing about distance on the real number line. In fact, I know I should. So, all right, back to distance for a moment on the real number line. What does it mean for A minus B to be less than, I don't know, 1? What does that really mean? So again, back to what I mentioned a few minutes ago, A minus B, what should you interpret this as? This is the distance between A and B, right? That's the distance, right? So what this means is that so for example, if I'm focusing in on A, right? So I'll ask another question, like, what B satisfy this? Right, if we fix A, what B satisfy this? Well, distance to A is anything that's a distance less than 1, right? So if I take A plus 1, open interval, and then over here would be like A minus 1, anything in there is within distance 1 to A. Anything in there is within distance 1 to A. So anything in this open interval will satisfy that. Okay? That's one way of interpreting this inequality. This inequality necessarily makes an open interval around A with radius 1 on each side. And if you can imagine a circle, the radius is going to be 1, right? So when you see distance less than a number, any positive number, you're necessarily looking at an interval around one of those numbers. Like if you fix that one and you're questioning B, it's like that. If you fix B and you question A, same thing. There's an interval around B of length of radius 1. And anything inside that interval will satisfy this. Okay? So I know that many of you won't take a course called discrete mathematics or won't take courses in programming, but a lot of mathematics is related to what's called logic. And we have to satisfy definitions according to some Boolean true or false value, right? So when we're looking at the definition, the formal definition of the limit later in lecture, we're going to be questioning whether or not some Boolean true or false thing is happening. Okay. Okay. So I'm going to pause the video and give my leg a break because I've been standing on it a little bit long. Okay, so we're back. And we're beginning the rest of this lecture by considering the following function. F of x equals to x cubed minus 1 over x minus 1. Okay. Now, in a pre-calculus course or an algebra course, you would notice that this is a rational function. It's a ratio of two polynomials. And also that there is a discontinuity at x equals 1, right? You can't plug in 1 here. If you do, you have division by 0, or actually, you have 0 over 0, which is a particular form that we will discuss later in the semester. It's called indeterminate form. This is bad. This means we can't evaluate the function, which in your previous classes might mean something like we just forget that function at x equals 1, right? What else, what other tools would you have to use, right? And I encourage you to really think about what you would have done if you encountered that in pre-cal or in algebra 1, or algebra, I mean, right? Like, it's almost like that thing just disappears when x is equal to 1, and there's no need to even consider it. However, what if we're observing some behavior that's described by this function? For example, we're observing how an object's distance from its starting place is changing over time, maybe. Or from a data science perspective, or a modern type, not modern, but yeah, a data science perspective, what if this was modeling the growth of some population over time? Or what if it was modeling the behavior of some machine learning algorithm, which that's what functions do. Machine learning is all about functions, if you ever heard that term before. So let's take a look at it. So on my screen, which I'm going to share right now, okay, let's move my little guy over there. On my screen, you will see a plot of this function. I made it look fancy for you guys, but basically what I'm using is the Julia programming language. I make a bunch of x's between -4 and 0.99, so not including 1, and I made 100 little points in there. I should say right x there. Actually, you don't even need that. So what am I making here? So here's my function definition. Notice how easy it is for me to write this function, x cubed minus 1 divided by x minus 1, using a little plot package. And then I'm going to plot f. Okay, so it's as easy as that. I just want to show f and I give it the label that. So that's the label that appears right here. And then I make, on top of that, I make a little hole. Okay, just to illustrate the discontinuity that happens when x is equal to 1. And again, I will make a video describing what I'm doing that all of you can go and watch later, and then also show you how to do this without Julia. So this is the graph of our function. It looks sort of parabola-like, right? And at x equals to 1, there's no value, right? It's like we're forgetting it. However, what is this missing piece here? There should be something there. It looks like we could fill it in, right? We could fill this in with some value, whatever this number is here that I've left out. And that's what we're going to try to figure out. In particular, we're going to consider if we keep on plugging in x's going this way, heading towards this discontinuity, where does the function go? Where is it heading to? What's its value? Whereas coming this way, we can start plugging in x's into this function that are getting closer to 1 from this side. And I want to see where the function is going this way and then where the function is going this way. It looks like they're going to meet up at some value. And maybe that's a good representation of what this function is basically at as x goes towards 1, that point of discontinuity. So maybe I have my f defined. So like, what's f of 0.75? So that's like over here to the left of x equals 1. It's 2.3. Okay. What about f of 0.9? We're getting closer to 1. So we're heading this way. 2.7. Okay. What about f of 0.99? Even closer to 1. Okay, let's get even closer. F of 0.999. So what is this telling us? 2.3, 2.7, 2.9, 2.99. Okay. Maybe this function is heading towards 3. Okay. Maybe. So the next thing we need to do is to check where it's going from the right-hand side. So let's look at f at something a little bit bigger, like 1.1. So it's bigger than 1. It's 3.31. Okay. What about f at 1.01? A little bit bigger than 3. So now we're heading this way. And then what about f at 1.001? Basically 3. So what this is telling me is that from the left-hand side, as we're growing towards 1, we're heading higher and higher. We're getting away from 2, we're heading towards 3. Right? And we get really close to 1. So this is like the x value, getting close to 1, right? It looks like we're getting close to 3. And then on the right-hand side, if we're over here, we're getting closer this way. We're also getting closer to 3. So what this is telling me is that I can get from the left-hand side as close as I want to 1. And as I'm going that direction, the value of the function is getting closer to 3. And then the same thing on the right-hand side, as I decrease getting closer to 1, I'm also getting closer to 3. So what this is telling me in an informal way is that something called the limit as x approaches 1 of this thing here it's going to be 3. This is a way of interpreting this function around x equals 1. Now, you have to pause and think about that for a moment, right? What does it mean to be around? Well, recall I just had a whole spiel about distance, right? So we can interpret this as, in quotes, because this is not exactly formal, when so maybe I should reword this a little bit. I can say that the distance between f of x and 3, right? That's the distance. The absolute value is the distance, right? The distance is small whenever x minus 1, distance, again, right? Distance is 1, right? So the input, right? Whenever this is smaller than some value. That's what we just observed, right? Now, when we were moving towards, so here's the plot, it looks something like this. When we were moving to x equals 1 from this side, we saw that we were getting closer and closer and closer. The distance between 3 and the function's value was getting smaller, right? And we could have gotten as close as we wanted to from this side and from that side. Okay, that's the notion of a limit. Now, notice what this is using. This is using distance. It's using that we can get close, meaning in between any two real numbers, there's another one. We're getting as close as we want to 1 from that side and as close as we want from that side. Those two things, right? We're using the Cartesian plane because there's distance around this value and there's distance around that value, right? And we're doing a sequential process. We're moving step by step by step by step and by step, right? And we're imagining we do this forever. We're imagining that we're continually getting closer on this side and on that side. And then what's happening up here on the y value? They're getting squeezed in as tight as we want around that value. There are 3. This is the idea behind limits. It's the informal idea. Okay. So, what about something like this? Another example. Maybe a piecewise function. So this function equals 1 whenever x is not equal to 2, and 0 if x is equal to 2. Okay. So we should be able to graph this thing. Now, I have to admit that coming from pre-calculus and from algebra and from trig, the functions that we might be dealing with in these examples are sort of the functions, no, they are precisely the functions that you avoided in those courses, right? Like discontinuity, you didn't even think about what it's doing by that discontinuity. Weird piecewise function. You didn't even really think about those for other than maybe one lecture. It's not going to be this way very long. But to introduce the concepts, we start with these weird things that you had no tools to work with in pre-calc. We're going to get to nice, smooth, continuous functions and polynomials and things like that, where understanding the behavior is easy. But I hope that this is a reminder that there are other functions out there other than these smooth-looking things. Like that's not smooth because there's a big hole right there. This is not smooth because there is a jump discontinuity, right? What does this function look like? It's 1 everywhere except for x equals to 2, where its value is right there. So there's 1. So it looks something like this. So this is the graph of that. Right? It's a piecewise function. There's these 2 pieces to it. So where does this function go as we head towards x equals 2? Right? If we're, what's the value? So like, what's f of 1? Like that right there. It's 1. What's f of 1.5? It's right there. It's also 1. What's f of 1.999? It's also 1, right? We can get as close as we want over here, but we keep on nudging up against the value 1 coming this way, right? So this is x heading that way. But what about x coming this way? It does the same thing, right? What's f of 3? it's also 1. What's f of 2.5? It's also 1, right? On both sides, as x is approaching 2, where is the function heading to? It's heading towards 1, right? There's no indication from the behavior of the function as we're observing how it changes as we change our x values heading towards 2. There's no behavior, nothing indicates that its value is going to be 0. The limiting process as we're getting closer indicates that it's heading towards 1. So that's an important lesson here. This function here has a limit of 1, even though its function's value at 2 is 0. So it doesn't match up with the function. Important note to make. Okay. All right. What about this next one? Let's look at the limit as x approaches 0 of the absolute value of x over x. Now, another weird function, right? Does this function here exist at x equals 0? No, right? We have 0 over 0. It's this indeterminate form that we haven't learned about yet, but if you're in pre-cal, you wouldn't know what to do with it, right? So let's see where this thing goes as we take x and we push it towards 0 from the left-hand side and from the right-hand side. Is there some value that it goes towards? Well, to help you, so these have the same value. So this function is either going to be -1 or +1, correct? Okay. The only difference between this and that is the sign. Okay. So this graph will look something like this. So here's 0. So when x is negative, like for example, -1, right? We'll have +1 over -1, so it's -1, it's down here. When x is -2, it's going to be +2 over -2, so -1 again. It's going to look like this. There's a hole right there. When x is positive, this is just going to always be 1, right? Except for at x equals 0. So looking from the graph, right? What can we say? As x is going this way, where's the function value always at? It's at -1, right? So I'll just make note of that. As x goes to 0 from the left hand side, it appears that f of x is going towards -1, right? Now, let's look at the values of f as we go from the right-hand side, right? So at 2, f is equal to 1, right? At 1, f is equal to 1. At 0.5, f is equal to 1. Whereas it seems like it's heading towards 1, right? As x goes to 0 from the right-hand side, f of x looks like it's going towards +1. Okay? And I think this is a good picture, right? -1, -1, -1, all the way, any value of x we pick this side, -1. Any value of x we pick on that side, +1. Right? When this happens, there's no like ultimate value. They're going to different values depending on what side you're coming from. So we'll say that this limit here does not exist because they go to different values. They never meet up. And I always forget when I teach calculus, I get to this point, and it reminds me of that movie Mean Girls, where Lindsay Lohan like finally realizes the limit doesn't exist, and it's like a perfect calculus question. Good movie, I like it. But yeah, so that's the case, and hopefully that helps you remember it too. If the limits don't match up, limits does not exist. Okay. All right. So what else can happen? Well, the function doesn't necessarily have to go to a specific number, right? For example, if we look at the limit as x goes to 0 of something like 1 over x squared. Okay. Another really important type of function. So we have 1 or some constant number in the numerator, and we have a variable in the denominator, right? Or some combination of variables in the denominator, which means we can't ever have 0 in the denominator, right? We have to avoid this division by 0 problem that will occur, okay? So what happens as we get closer to 0 in this case? Well, if you think of it from the positive side, I guess like here's like 1, here's 2, blah, blah, blah. But we're like down here, we're dividing by 1 divided by 2 is a half, 1 divided by 1 is 1. But then, like right here, a half right there, 1 divided by, so 1 divided by a half squared is 4. 1 divided by 1 over 10 is 100 in this case because we're squaring it, right? It starts blowing up, right? So it's shooting up to infinity. The closer we get to 0, we can make the largest number we want possible, right? We pick a small enough positive number, this is going to be huge. Now, because it's being squared here, the same thing happens over here. It's symmetric about the y-axis. So there is no number, right? If we go to x equals 0 from this way or this way, where is it going? It's going to infinity. So we'd say that this is unbounded. Okay. Now this can be a huge problem. For example, for those of you that might like physics and general relativity, this behavior of like going to infinity like this occurs at points of singularities in black holes, for example. It blows up. Nothing will work anymore at that point. Right? And it's essentially because of division by 0, and you can tell that it blows up by observing the behavior as you tend towards a given value. So this is another thing that can happen when looking at limits. Okay. And then finally, another odd behavior to observe is oscillation. So if we're looking at the limit as x goes to 0, the sine of 1 over x, this is going to oscillate forever. It's going to look something like between 1 and -1. Like this. This is going to oscillate between 1 and -1. If we keep, no matter how close we get, there's never going to be a definite value that we'll encounter. Right? So this is another type of behavior where the limit does not exist. Unbounded, I should probably have said, does not exist. There's no numerical value. This is oscillation. So and those kind of summarize all the problems you might run into. Okay. Now, finally, I'll introduce the formal definition, which we will go over in detail next time. I feel so dumb just scooting around on my leg. All right, formality time. Okay. Let f be a function defined on some open interval containing a number c. And I'll say that f at c might not exist. Okay, so f is just some function. You know what open intervals are? They're just some continuous value of numbers between a and b, not including. So, oh, one more thing. And let L be a real number. Okay. Now, bear with me on this formal definition. Hopefully it will all make sense. We say that the limit as x approaches c of f of x is equal to L. Okay. Whenever for any epsilon greater than 0, there exists a delta greater than 0 such that x minus c less than delta implies f of x minus L less than epsilon. Okay, lots of fancy math stuff that is just hiding the general idea that I think that is important, which is always the case. And I should probably have a disclaimer, or not disclaimer, but I should have a remark for all of you going forward in your undergrad degree, that a lot of times you're going to, in a lot of your math courses, you're going to encounter wording and notation that is intimidating or different. It's much different than like the way that we talk to each other. It's very formal, but you have to try and remember that behind this formality, there's an idea. Mathematics is all about ideas. And this definition is trying to explain an idea, right? So that's why I kind of made sure that we were on the same page when it came to what it means for distance to happen on the real number line, so that we can understand this. Now, let's go through it. F is a function defined on some interval containing that number C. L is some number. And we say, in the formal sense of the word, that the limit, or the notion that the limit of f of x as x approaches c equals L whenever the following thing is true. This condition is met always. It's a Boolean statement, like I mentioned before. It's either true or false. If it's true on this side, then we can write that and we're justified. That is the definition that humans decided, mathematicians decided was the appropriate one. Okay, what's on this side? For any epsilon greater than 0. Now, in mathematics, mathematicians tend to use epsilon to represent a small value. Okay, so think of epsilon as just some really small number. Okay, so for any choice, you pick your epsilon, no matter how small it is, as long as it's greater than 0, just any small epsilon. There exists some other number, delta. Okay, now it's not necessarily explicit in the definition, but what's really happening is once you choose an epsilon, you get a delta. Okay, there is one for this to be. If this is true, there better be one. It's dependent on that choice, such that what? The distance between x and c, whenever that distance is smaller than this value, delta, then the distance between the function and the limit is smaller than that choice of epsilon. It helps to say distance out loud when looking at these things. So remember what I said about the interval around x, or the interval around c in this like absolute value earlier? So what this is really saying pictorially is something like this. Going back to the very first example that we had, which was f of x equals to x cubed minus 1 over x minus 1, right? This function looks something like that, whatever, okay? So we know, because we did this earlier, that the limit of this function equals 3 as x approaches 1, right? We figured that out. So let's make sure that it satisfies this statement right here. So pick any epsilon that you want. Any epsilon greater than 0. Okay. And then look right here. This is the distance between the function and the value L. This is like my L. And this is my C. Okay. So how can we interpret this? What values of this are within epsilon to L, right? It's like an interval, like I was trying to emphasize earlier, right? So I can do like L plus epsilon, L minus epsilon. Remember, it's a real number line, right? So we have some interval around epsilon, okay? Now, because this is true, there better be a delta so that this is satisfied. What are the values of x that satisfy this? It's all x that are within that little interval around c. So this could be like c plus delta. This could be like C minus delta. Again, distance, right? So in this kind of ugly looking picture, is it satisfied? Well, if this is satisfied, that better be true. So pick any x you want in here. Oh, my delta is wrong, by the way, because if I pick an x there, that's the value of the function that's not in that interval. You see that? And this better be true. I better pick the right delta. So maybe here. Smaller interval around C. Now, this is satisfied, I'm pretty sure. Pick anything that, pick any x that satisfies that, like right there. What's the function's value? It's inside that interval. Pick another one, pick right there. It's in that interval. And this was for this big choice of epsilon. If we made a small, tiny little choice, like, let me see if I have another color, blue, like, there's the L. If I pick like a tiny little epsilon interval, L plus epsilon, L minus epsilon, right? I can find a tiny little interval around C so that if I pick a value in there, it's in there. Pick any value in there. I'm kind of cheating a little bit, but you get the idea, hopefully. Okay? So that's what all this epsilon delta business is saying. It's saying that no matter the small little ball that you put around your limit, no matter how small the radius is, that's what that is, distance, right? No matter how small that little ball is around there, there's something in the domain, there's a little interval around that C in the domain, such that every single value that you pick in there and put into that function is squished in there. And there's an infinite number of things in there that are squished inside there. Which, if it's squished on both sides, which this would imply because this distance is both up and down, right? Squished on both sides, it means that if we get arbitrarily close, we can get arbitrarily close to that limiting value by squeezing around the C. And that's it. That's the idea of the limit. Now, I'm not going to ask epsilon delta type problems on any exam, but I'm going to put epsilon delta problems on the homework and then make a separate video showing you how to find the appropriate delta if you're given an epsilon. Okay, I don't want to cover that in class, but for those of you that are math majors or minoring in math, this is kind of important to do because this will appear later on. Okay, so that will be it for this recording. I'm going to go ahead and stop. Thank you for watching.